How's the board look? Fine?
Yeah, that looks better.
Cool, good. So, polynomial division. What do you multiply by x to get x squared? You multiply x. X times x is x squared. X times negative 6 is negative 6x. We subtract. X squared minus x squared is 0. I don't usually write anything there. 3x minus 6x is 9x because it's 3x plus 6x. Bring down the next term, and then we say, what do you multiply by x to get 9x? And the answer is 9. And then you stop. Once you've got the constant term up there, you're done. Your slant asymptote is y equal to x plus 9. Let's go ahead and graph this one, even though it's not very nice. So, yeah, let's go to the other side. So I was going to graph f of x equal to x squared plus 3x plus 1 over, what did I just say, x minus 6. This kind of looks like it could be done. It's time to start getting rid of some trash pens. Probably said that yesterday too, and then I didn't. So we found the slant asymptote. It was y equal to x plus 9. Let's find the y-intercept. So set x equal to 0. If x is 0, you're going to get 0 plus 1 on top, and 0 minus 6 on the bottom. So negative 1/6 is my y-intercept. X-intercept are not going to be nice. We're going to set the top equal to 0, and that does not factor, but we can use the quadratic formula to get x equal to negative 3 plus or minus the square root of 3 squared minus 4 times a times c, so 4 times 1 times 1, all over 2 times 1. So we end up with negative 3 plus or minus the square root of 5 all over 2. That's not very nice, but it's fine. We'll deal with it. And then finally, we have a vertical asymptote at x equal to 6. A couple things about my asymptotes and my intercepts. So my vertical asymptote is an odd multiplicity, right? It's a degree 1 vertical asymptote because this has a multiplicity of 1. So it's going to be an opposite, right? One side up, one side down. And then these x-intercepts, there's 2 of them. There's negative 3 plus the square root of 5 over 2 and negative 3 minus the square root of 5 over 2. And they also both have odd multiplicity because if we had factored this, we would have gotten x minus one of these things to the first times x minus the other one of these things to the first, and then we cat out. Yes, I know. I started teaching and now you must leave. Okay. She's so weird. She's just chilling in her basket, and then as soon as I start teaching, it's like, oh. So whenever you find, whenever you have a quadratic and you find 2 distinct solutions to that quadratic equal to 0, they're both going to be intercepts of multiplicity 1, meaning we're going to cross both of those. It's kind of like, right, if you're actually graphing a parabola and you found 2 different x-intercepts, the parabola would cross the x-axis at both of those intercepts. Same kind of idea. Is that 9 minus 4 times 11? No, that's 9 minus 4 times 1 times 1. Right? It's b squared minus 4 times a times c. So graphing this thing, we've got a y-intercept of negative 1/6, so very, very slightly negative. We've got a slant asymptote of y equals x plus 9. That's going to be kind of, let's just draw it like here. I'm not thrilled about this graph. So how do you just make things up? So here's 0, 9, here's negative 9, 0. Got this one here. And then, see, negative 3 plus the square root of 5 is still a little bit negative, right? Because the square root of 5 is like 2 point something. So negative 3 plus 2 point something is still slightly negative. So you're going to have one x-intercept that's slightly negative. And then negative 3 minus the square root of 5 is more negative, right? It's negative 3 minus 2 point something. So like negative 5 divided by 2 is like negative 2 point something. So I don't know. It's like, maybe it's like over here. Right? I'm not drawing this very precisely. And then I have a vertical asymptote at 6. So let's say like way over here. So I've not set this up well. Let's try again. So sometimes you look, so actually let me kind of back up and talk about why I'm doing it again. So if you look at this, here's what's going to happen. It's going to go down this way to the right, and then the other side of the vertical asymptote is going to be up here, but it has to be kind of over that part there. And then over here, it's going to cross, and then go down that way. So we've got kind of the vague idea of what's happening, but we could have set ourselves up for better success. So here's what I actually really want. I want more space up here. So let's draw it like over here. That's dumb, James. I still need space to the left and to the right. So, okay. Make it big. So let's say here's my slant asymptote. Y equal to x plus 9. Here's my vertical asymptote at x equal to 6. Here's my y-intercept that's very small. Here are my x-intercepts, which are, and then it's going to do this kind of deal. So to the left, it's getting closer and closer to my slant asymptote. To the right, we go down, and then on the other side, we're up here. That's wrong like that. So that's how I would graph this one. And then I would probably label the points, right? I'd be like, okay, this here is 0, negative 1/6. And I'd probably be kind of lazy about these other ones and say, okay, these points over here are the negative 3 plus or minus the square root of 5 all over 2. Again, this was just kind of an example, not a great example. Usually the examples that we have, like the next few ones, will have nicer x-intercepts and maybe not such extreme slant asymptotes. You are not required to label where the slant asymptote crosses the axes. You definitely need to know what it is so that when you graph it, things look right. Like you should know that it's going to cross the y-axis at 0, 9 and the x-axis at negative 9, 0. But you don't have to label those points.
Can I ask you a quick question?
Yeah, go ahead.
So when you graph a slant, do you just draw it as just a diagonal line where for this problem 9 would be on the x-axis?
Negative 9 on the x-axis.
Negative 9.
Yeah, so if you label those points, the slant asymptote would have a y-intercept of positive 9 and an x-intercept of negative 9.
Gotcha. Thank you.
And whenever I'm graphing a slant asymptote, I'm always thinking of the way I'm graphing it is thinking about where would its intercepts be. That's kind of the easiest way.
Gotcha. Okay.
Let's look at a more reasonable example. And I'll point out on this template, it usually has you find the slant asymptote first. Usually I'm kind of finding the slant asymptote last, just because that's kind of the way I usually do it. So let's try graphing f of x equal to x squared over x cubed over x squared minus 9. All of these x cubed over x squared minus 9. And I will just point out, we know there is a slant asymptote because the degree on top is 3, which is exactly 1 larger than the degree on the bottom, which is 2. So if the difference is 1, where the top is the bigger one, it's a slant asymptote. I will also just remind you guys that if it were this function, x squared minus 9 divided by x cubed, that would have a horizontal asymptote of y equal to 0 because the degree on top is smaller. Okay, so let's find all the things. Y-intercept. We set x equal to 0. Y is going to be f of 0, which is 0 over 0 minus 9, which is 0. X-intercept. We're going to set the top equal to 0. We're going to get x cubed equal to 0. We're going to get x equal to 0. I will point out that this x-intercept has an odd multiplicity, the multiplicity of 3. So the graph is going to cross the x-axis at the origin. Let's try and find the vertical asymptotes. We're going to set the denominator equal to 0. So x squared minus 9 equal to 0. I think it's best to factor it. We're going to get x minus 3 times x plus 3 equal to 0. So we get vertical asymptotes at x equal to 3 and x equal to -3, and they both have odd multiplicities as well, meaning that one side's going to go up, the other side's going to go down, the opposite. And then finally, we don't have a horizontal asymptote because the degree is larger on top than it is on the bottom. But we do have a slant asymptote because the degree on top is exactly one larger than the degree on the bottom. So our slant asymptote we're going to find by doing polynomial division. I will mention, if you want to and you really like using synthetic division, you are welcome to do so. But I will point out synthetic division does not work in this example. You can only use synthetic division when you are dividing by something that's like x minus 2 or x plus 5. So the synthetic only really works if you have a degree 2 on top and a degree 1 on the bottom. If you don't like synthetic or have never heard of synthetic division, don't worry about it. It's not that important. But and I'll say, like when you take the second quarter of calculus, when you are doing some polynomial division again for reasons that I will not mention right now, you usually want to do the polynomial long division, which is what we were doing in class. But if you like synthetic, that is also fine, and you can use it when appropriate. So to do this division, I'm going to write out x cubed divided by, and I'm going to fill in the missing terms. I'm going to write this as x squared plus 0x minus 9, and I'll write plus 0x squared plus 0x plus 0. It's just nice to have all the lower powers of x so that we don't, so that when we write this out, we don't things line up correctly is what I'm trying to say. So x times x squared is equal to x cubed. X times 0x is 0x squared. X times -9 is -9x. Subtract, you get 0. You get 0. 0 minus minus 9 is 9x. And then we ask, what do you multiply x squared to get 9x? But 9x is a lower power, so we stop. So our answer here is just x. That's our slant asymptote. You see there's a question here. It's SOP when graphing to get the root. I'm not sure what SOP means.
Like standard, like that's the first thing you do basically whenever you're trying to graph or figure out.
I would say that's my standard operating procedure. It's really like we have to find all these things. I typically find the intercepts first and then the asymptotes later. I typically don't really think about the domain and the range, like they're kind of in the background. So I know that because we have vertical asymptotes at 3 and -3, those values are not in the domain. I'm usually not thinking about range really at all, to be perfectly honest, when I'm graphing something. Yeah, I would say intercepts, asymptotes, kind of thinking about domain a little bit. Yeah, that's my standard operating procedure. I might also think about, if I'm lucky, sometimes I notice if a function is even or odd. I would point out that this function actually is odd. If you plug in -x for x, you get -x cubed over -x squared minus 9, which becomes just -x cubed over x squared minus 9. So this function does have the odd rotational symmetry about the origin. But if we don't see that, that's okay. So let's draw the thing. I feel like these ones, I need a whole board just for drawing. Because that's the way it's going to be. Do try and give yourself enough room when you're doing problems like this to draw your graph so that you can indicate what. So let's see. I've got vertical asymptotes at 3 and -3. And a slant asymptote of y equal to x. The only one that's going to have, like one intercept. And then what else have I got? I think that's it, right? Y-intercept, X-intercept, 0. Oh, I've got an intercept of 0. Notice, and I'll point out, just like with a horizontal asymptote, a graph can cross its slant asymptote. Like in this example, it's definitely going to cross it. So let's see. So I would probably, the problem here is like, I don't know if it's going down this way or up this way. It could be either. So let's plug in the point. So again, our function is x cubed over x squared minus 9. If I plug in 1, I get 1 over 1 minus 9, which is going to be -1/8. So I know when I plug in 1, I get a slightly negative value. So we're going to have to go down to the right. And then on the other side of the vertical asymptote, well, there's a couple reasons we have to be up here. One, the asymptote had an odd degree, so it's going to be the opposite. If it's down here, it's up here. Two, we have to get closer to the slant asymptote. It could generally be possible to be down here and then come up this way like that. But the problem is we don't have an X-intercept there, so we can't do that in this particular case. So we have to be up this way and then like that. On the other side, well, we know that the X-intercept was across, meaning if we're below here, we have to be above over here. You can also plug in -1 and see that you get -1 over -8, which is +1/8. And then we have the same sort of asymptote being odd. So if we're up here, over here, we're down here. And then we have to turn around somewhere and get closer and closer to our slant asymptote. Again, we are not responsible or able to find these points where it turns around. So don't worry about trying to find those. Yeah, SA is slant asymptote. Yeah. Also called an oblique by some people. So that's pretty much the whole graph. Notice it is an odd function, right? Like I don't typically look for that, but if you think about this, if you were to rotate this 180 degrees, it would look the same. It's too bad the board doesn't rotate that way. That'd be kind of a cool board to see. If I was trying to show rotational symmetry, be like, hey, look. Anyway, that's not what we have here. But it's kind of cool. I'm gonna look at. I know you guys can see this, but I'm looking at it on the other side, and it totally looks like, yeah, that's kind of neat. It looks like I reflected in the x-axis, which is, you guys are like, well, big deal, we can't see it, but okay. It does kind of look like, it looks like I did the reflection this way, but this way, because they're the same if it's a non-function. Okay. But I know that doesn't really help you because you couldn't see it. I could literally turn the board around, but it's not really that interesting, so I'm not going to. That's the downside of having my board on carpet here. My coworker, she has her board, and every time she turns around, she does a flip like this, which requires wheeling it around, but it does have some advantages. Like I could totally write stuff on the other side of the board without what being behind it, and then turn around, you can see it, and it would be upside down. Anyway, that's not what we're here to talk about. Let's do some more examples. Again, all these are going to have slant asymptotes because they're all going to have a degree on top that's exactly one larger. So let's look at, say, this lovely looking function, f of x, x squared minus 4 over x minus 1. We're still going to go through the usual list of things. But we definitely recognize from the get-go, oh yeah, there's a slant asymptote because the degree on top is exactly one larger than the degree on the bottom. Let's find the usual things. Y-intercept, f of 0 is -4 over -1, which is 4. X-intercepts, so the top equal to 0. Notice, by the way, that this is a quadratic, if I'm just thinking of the top on its own. So if I have distinct intercepts, they're going to both cross because they both have to be degree 1. I am going to have distinct intercepts. This factor is x minus 2 times x plus 2. So I get x equal to 2 and x equal to -2. Both of the multiplicity of 1. Meaning it's going to cross the x-axis 2 times. Vertical asymptote, x minus 1 equals 0. You get x equal to 1. Also with an odd multiplicity, meaning we've got this kind of deal happening again, one side up, one side down. And then finally the slant asymptote. I wish I could fit it down here, but I can't really. So we got to do the polynomial division. X squared plus 0x minus 4 divided by x minus 1. We multiply x by x to get x squared. So x times x is x squared. X times minus 1 is minus x. We subtract. This minus this is 0. That's why we picked it in the first place. 0x minus x is x. Bring on the minus 4. And then when you multiply by x to get x, you get 1. And then we stop. As soon as you get to the constant term up there, you're done. That means your slant asymptote is y equal to x plus 1. You don't have to finish this polynomial division. I think we can fit this all. The other thing I want to say is this graph isn't odd or even, right? If you plug in, not that you need to check this, I don't think you ever need to check this, but just to kind of point it out, if I look at f of negative x, it's negative x squared, which is just x squared minus 4 over negative x minus 1. This definitely isn't the same as the original function. And it's also definitely not equal to negative f of x. Because negative f of x would be negative x squared minus 4 over x minus 1. And if we distribute the negative to the bottom, you get x squared minus 4 over negative x plus 1. And that's not the same as that either. Just want to point out, right? We don't usually look for it, but it is maybe worth mentioning here. It's not odd and it's not even. So we're not going to have any kind of nice symmetry. Oh, well. So let's graph the thing. Let's see, 1, 2, 3, 4, 5. Sure, I'm just making marks. Let's see, I've got a y-intercept of 4, x-intercepts at 2 and negative 2. Vertical asymptote at x equal to 1. And the slant asymptote of y equal to x plus 1, which means it's going to go through the point, right? It's going to go through the point 0, 1, when x is 0, y is 1, right there. And negative 1, 0, when y is 0, x is negative 1. It's right there. So it's going to go. And you don't need to know where these cross, but the asymptotes would cross at the point 1, 2, which I have not drawn very well. Oh well. Okay, so then I'm going to start at my y-intercept. And I usually move to the right first just because that's what we do. So as I go this way, the first thing I encounter is this vertical asymptote. So I have to kind of go this way. I should also say, just like with horizontal asymptotes, you really don't think about the slant asymptote having an effect until you're way out to either side. On the other side of this vertical asymptote, we have to be down here because, again, it's an odd multiplicity vertical asymptote. So we're going to be down here. And then we're going to come up. We're going to hit this point. We're going to cross. And then we're going to do that, getting closer and closer to the slant asymptote. Yeah, so the vertical asymptote is always based on setting the denominator equal to 0. Another way to think about it is the vertical asymptote is the places where the function is undefined, right? The function, there isn't actually any x value, right? If you plug in positive 1, you get negative 3 divided by 0, which is undefined. As you get closer and closer to 1 from either side, the values get very, very large, very, very negatively large. So just kind of, yeah, let me go with that for just a minute here. Right? If I were to plug in something crazy like, I don't know, if x were to be 1.001, for example, then my y value would be 1.001 squared minus 4 over 1.001 minus 1. The top, in fact, I can even get out a calculator if we really want here. 1.001 squared minus 4 is negative 2.997999. I don't really care about that. It's negative 2.997999. Divided by 0.001 minus 1 is 0.001, which is 1/1000th. When you divide by 1/1000th, that's the same as multiplying by 1,000. So if you take negative 2.997999 and multiply by 1,000, you get negative 2,997. So on the right-hand side, when x is very, very close to 1, when x is like 1.001, the y value is negative 3,000 almost. And the same sort of thing happens on the left. If x was 0.99999, then the top would be very close to negative 3, and the denominator would be very, very small, but negative. So it'd be like negative 3 divided by negative 1/1000th, which would be like positive 3,000. So that's what's happening. So you get, yes, you get the vertical asymptote whenever the denominator is 0. I should say, You get a vertical asymptote whenever the denominator is 0 and the numerator is not 0, because 0 over 0 is a slight. Anyway, so then if we're continuing the graph, we're going to go to the left. And so I didn't draw this very well. Because I kind of drew my curve like it was coming down that way, but I need to hit that point. So I would probably erase all of this and maybe try and fix it. So I know I'm supposed to go through this point and also kind of get close to this. So it's going to kind of do this like that. It should be smooth, for lack of a better word. Like there shouldn't be like weird kind of jagged turns in your graph. Like polynomials, rational functions, where they're defined, are differentiable, meaning they're smooth, there's no sharp turns or edges or corners.
Can I ask about the long division problem?
Sure.
How did you get in the second part of the problem where you had x squared minus x? Can you explain how you got that minus x?
Totally. So once you've decided that x goes up here, because you know that you need x times x to equal x squared, you're multiplying this x by everything here. So you do x times x minus 1. X times x is x squared. X times minus 1 is minus x.
Oh, right, okay.
And that's always the case for polynomial division. You're always multiplying whatever's on top by everything that's in the divisor.
Right, thank you.
You're welcome, of course. Let's look at another example. I know I said it yesterday, but I'll remind you guys again. I'll remind you guys on Thursday and Friday too. There's no class on Monday. Don't go to your classes on Monday. Okay. Let's look at this next one. Let's look at f of x equal to x minus 2 squared divided by x minus 3. Maybe I'm gonna change this one up just slightly, just to make it a little more interesting. It might not be very exciting, but I'm gonna change this to the following. I'm going to change it to, I'm really just going to multiply the top and bottom by x plus 4. So I'm going to write this as x minus 2 squared times x plus 4 divided by, I forget what the denominator was, x minus 3. So it's going to be x squared plus x minus 12. So here's a slightly different, really just very slightly different problem that's still going to be the same as what I had before with one exception. So here's the thing about this. We have to be careful. Let's pretend like, I'm gonna pretend like we didn't know it should factor and cancel. So let's start doing stuff like we normally would. So if I was gonna find the y-intercept, y-intercept's still gonna be all right. I set x equal to 0. I'm gonna get f of 0 is, let's see, 0 minus 2 squared is negative 2 squared times 0 plus 4 is 4 divided by 0 plus 0 minus 12. So I get 4 times 4, so 16 over negative 12. I can cancel a factor of 4 and get negative 4 thirds. Okay, we're fine so far. Here's where we're about to run into a small problem, which we'll address in a minute. I look at the x-intercept, so I'm going to see, okay, well, I want where the numerator is equal to 0. So x minus 2 squared times x plus 4 equal to 0. I'm going to get x equal to 2 with an even multiplicity, which means it's going to bounce there. I get x equal to negative 4 with an odd multiplicity, meaning it's going to cross there. Okay, but now my vertical asymptotes, I'm going to set the denominator equal to 0, around where the function is undefined. So x squared plus x minus 12 equal to 0. This factors as x minus 4 times x plus 3. And here's what if I'm not paying attention, I'm going to be like, okay, well, I'm going to have a vertical asymptote at x equal to 4 and a vertical asymptote at x equal to negative 3. And here's what I want you guys to see. If you have a place where you have a vertical asymptote at x equals, sorry, ooh, did I make a mistake? I did, I factored that wrong. Ooh, wow, we're making big mistakes here. So this mistake is really important to not make, because if I did this, I wouldn't see anything wrong. I'd be like, oh yeah, things look fine. I've got some vertical asymptotes, I've got some intercepts. I did make an error though, I factored this wrong, right? Because negative 4 times 3 is negative 12, but negative 4 plus 3 is negative 1, I need a positive 1. So this should have actually factored as x plus 4 times x minus 3. Woo. making big mistakes, which means my vertical asymptote should actually be x equal to -4 and x equal to +3, both with a multiplicity of 1. Here's what I want to point out. If you're doing a problem, a rational function graphing problem, and you find a place where you have an x-intercept and a vertical asymptote that are the same, that means you probably don't have either, actually. But what it really means is that factor where those both came from should have canceled. Right? We should actually look at this and say, oh, this is x minus 2 squared times x plus 4 over x plus 4 times x minus 3, and those x plus 4's cancel out, which means this is equal to x minus 2 squared over x minus 3, and we have a whole at x equal to -4. It also means that we don't have a vertical asymptote at x equal to -4. Because if you look at this reduced version, -4 doesn't give you division by 0. It also means we don't have an x-intercept at -4. Because if you look at this reduced version, setting the top equal to 0 doesn't give you -4 as an answer. In this case, we would do the factor of the bottom. Yeah, totally. So that's so what I'm Zaina, actually, you've summed it up perfectly. That's why you want to factor and cancel before you do anything else, so you don't see these not actual real x-intercepts and vertical asymptotes. So you should always look to see if you can factor and cancel anything first. But if you forget to do that and you run into this problem where you have a vertical asymptote and an vertical asymptote and an x-intercept at the same place, that means you should go back and factor because something is going to cancel. What do the holes do, Paula? So the holes we'll do the whole graph, pun intended. We'll do the whole graph, and then at x equal to -4, we will just take out the 1 point and draw a little open circle. That's what the hole is going to do. Okay, so let's find the slant asymptote, and then we'll graph the thing. It's also going to be nicer to do the slant asymptote for this versus this, right? Because for this, we would have had to multiply off the top, which would have been not fun, and then divided by the bottom. Here, we can say, okay, we're going to have this divided by x minus 3. You do actually still have to multiply at the top, though, to do the polynomial division. So x minus 2 squared is x squared minus 4x plus 4. X times x will give you x squared. X times all of this is x times x is x squared. X times minus 3 is minus 3x. Subtract. Bam, 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 0. -4x plus 3x is -x. X times -1 will give me -x. Stop. You're done. That's your slant asymptote. Okay, so now we're going to try and graph the whole thing. And I'm literally going to ignore that there's a hole until after I've done everything else. So again, we're graphing f of x equal to x minus 2 squared over, what was it, x plus 3? X minus 3. And we know that x is not allowed to equal -4. Right, that's where we're going to have a hole. So let's see what we had here. We had y-intercept of -4/3, x-intercept of +2, y plus minus 1. Okay, cool. I don't usually like making all these marks when I'm graphing lots of things, but rational functions, I think, are kind of the exception. They usually need to be having all this. The slant asymptote is y equal to x minus 1. Just whatever the quotient is when you do the polynomial division. So let's graph the thing. So let's graph the slant asymptote. So y equals to x minus 1. It's over here. Would have a y-intercept of -1 and an X-intercept of +1. So it looks like that. And again, right, these are not actually points on the graph necessarily. They could be, but they don't have to. They're not usually points on the graph. And then let's see, our X-intercept was +2. Our Y-intercept was -4/3. I think, right? Let me check. Yep. And then our vertical asymptote was x = 3. Okay. So starting at my Y-intercept, I'm going to go to the right. I'm going to hit that point. I'm going to bounce off because it was even multiplicity and then go down this way. My vertical asymptote was an odd degree one, right? X - 3 is just raised to the first power. So if this side's down, this side has to be up. And then we're going to go like that. To the left, we just have to get closer and closer to the slant asymptote, like that. It's not perfectly straight, but it looks kind of straight the way I drew it. Okay, so I've drawn the whole graph, but now we have to remember, oh wait, x is not allowed to equal -4. So I'm going to go over here to -4, and I'm going to go down, right there. And I'm going to erase and draw like a little open circle. Now, usually it is proper to find the y value of your hole. So this hole would be at the point -4, comma. If I plug in -4 to the form where the x + 4 factors are canceled out, then I can say, well, let's see, I would get, -4 - 2 squared over -4 - 3. That's -6 squared, so 36 over -7. That's whatever that is there. Usually we find the y value for where the hole would be.
Are there like practical applications? I mean, I just want to know like what the whole like actually does, like like if you're calculating for something like a measurement or something like that. I don't know.
So really the idea of a hole here is going to come up when we start talking about limits in calculus. So like later on, someone's going to ask you a question. They're going to say, like, for this function, what's the limit as x approaches -4? Meaning, so that question really asks you, what y value does this function get closer and closer to as x gets closer and closer to something? So most of the time, that question is easy to answer. Like if I said, what is the function getting close to as x is getting closer and closer to 2? Well, that answer would be super obvious. As the x values get closer and closer and closer to 2, the y values get closer and closer and closer to 0. Or I could ask, what does the function get close to as x is close to, I don't know, 4. And so like right over here, as x is close to 4, the y values get closer and closer to whatever that number is, right? If you plug in 4, you're going to get 4. You're going to get 4. But it also works even if the point is undefined. So I could ask, what's the function getting close to as the x values get close to -4, and the y values are getting close to this value? They're not actually ever equal to that value, but they're getting close to it. So I don't know if that's a practical application, but it's certainly an important application that we will explore when we talk about limits, which is kind of the whole basis for how calculus works.
Thank you.
You're welcome. I know it's not a great answer to your question. Like I definitely feel like your question is coming from a practical application of like, what can this be interpreted as? I don't know if I have a great answer to that question. All right, let's do one more example. You're welcome. Let's do one more and then call it a day. So let's graph this one. Oh, let's get this gross stuff off my fingers. Y equal to x cubed minus 3x squared over x squared minus 2x plus 1. And let's learn some lessons from the previous example. Let's go ahead and factor as much as possible to make sure nothing cancels. So factoring it, I can factor out an x squared from the top. I'm left with an x minus 3. The bottom, x squared minus 2x plus 1 factors is x minus 1 times x minus 1, which is x minus 1 squared. Great. Nothing cancels. Y-intercept. If x is 0, y is going to be 0 times -3 divided by 1, so 0. X-intercepts at the top equal to 0. X squared times x minus 3 equals 0. You get x equal to 0 with a multiplicity of 2. It's going to bounce at 0. And you get x equal to 3 with a multiplicity of 1. So it's going to bounce here. It's going to cross here. My vertical asymptote, or asymptotes, but I only have one. I'm going to get from setting x minus 1 squared equal to 0. That's going to give me x equal to 1 with a multiplicity of 2. Meaning my vertical asymptote is both sides are going to go down or both sides are going to go up. Okay, we're going to have this or this. All right, that's what's going to happen when you have an even multiplicity vertical asymptote. And finally, we do have a slant asymptote because the degree on top is one larger. So let's do the polynomial division to find the slant asymptote. So here's the thing, right? You don't want the factored form when you're doing the division. You want the unfactored form. So I'm going to do x cubed minus 3x squared plus 0x plus 0 divided by x squared minus 2x plus 1. So then what do you multiply by x squared to get x cubed? X. Most of the time, the answer is going to be x up here. Sometimes you might have a polynomial where, like, if this was a 2x cubed on top, then you'd end up getting a 2x here. If we have time, I'll do one more example at the end, just with the division. So then x times x squared is x cubed. X times negative 2x is negative 2x squared. X times 1 is x. Subtract. Right, you're multiplying x by all of this. This minus this is 0. Negative 3x squared plus 2x squared is negative x squared. 0x minus x is minus x. Bring down to 0. What do you multiply x squared to get negative x squared? It's going to be a negative 1. And then we stop. There's your slant asymptote. Y equals x minus 1. Now we're going to graph it. Let's see here. So we're graphing it. I know it's on the other side. Let's see. What do we have here? I can look at my notes. We had y-intercept of 0, x-intercepts of 0 and 3, a vertical asymptote at positive 1, and a slant asymptote at y equal to x minus 1. So y equal to x minus 1 would go through the point 0, negative 1, and positive 1, 0. So here and here. Is that all we've got? That's all we've got. Yeah, let me double check. Y-intercept, x-intercept. Okay. We know our vertical asymptote is both up or both down. We know we're bouncing at 0, crossing at 3. Now here's the issue. We kind of need more information, right? Because I don't know if this goes up like this or down like this. I could go to the right, but if I go to the right, I'm going to have to plug in something like 1/2, which is fine. But if I have the option, I would rather maybe plug in something that is a little bit easier. So instead, we could go to the left. If we go to the left, if I plug in negative 1, y is going to be, let's see, negative 1 squared times negative 1 minus 3 over negative 1 minus 1 squared. That's going to be 1 times negative 4 over negative 2 squared is positive 4. That's going to be negative 1. So I actually get the point, minus 1 minus 1. So that means it's down on this side, which means it's also going to be down on the right side because it bounces, right? If we're doing this, we have to bounce and do that. Which means we cross our slant asymptote. That's okay, it happens. To the right, continuing on, right? Left side was down, the right side's down. And then we're going to cross, and then we're going to get closer to the slant asymptote. So we're going to do something like this. On the left side, I should finish off this. So this is going to bounce here, and then it kind of has to like kind of do this turning around kind of thing. You might try graphing this on Desmos just to see what it actually looks like. But there is kind of a weird, strange turn there, which is fine. So yeah, that's how that